So our third speaker is GZoppi, who is also a PhD student at the University of Turin in Italy. And we are moving up a scale in terms of both species and modeling. We are now looking at Italian buffalo movement networks, qualitative analysis and impact on disease diffusion. Ready to go, Giacomo.
You can see both me and the screen?
Yes, all good.
Perfect. Good morning, I'm GZoppi, and as suggested, I will talk about Italian buffer movement network. And the work has been done by the Data Analysis and Modeling Unit of the Department of Veterinary Science in collaboration with the Istituto Zooprofilattico Sperimentale dell'Abruzzo del Molise. In this presentation, I will talk about buffaloes. But a first question that could arise here is, why buffaloes? Well, first of all, buffalo farms are an important productive reality in Italy. For example, buffalo mozzarella is one of the most common dairy products that you can find here, one of the most famous also. In the plot on the right here, you can see the map of Italy, and the purple color denotes the number of buffalo nodes in each region. The dot blue point instead denotes the number of nodes that shares the farms that shares their space between both bovines and buffaloes. Actually, more than 60% of the farms breeds both the species. We can see here how the prevalence of the animals are in the central southern part of Italy, but anywhere are spread in the whole peninsula. We will try to answer to the following question in this presentation, that is the properties and the characteristics of this buffalo network. And also we will try to answer if this network can support the spread of a pathogen. Now, the dataset that we use is a 4 years dataset that goes from 2017 to 2020, and is divided into two datasets. The first one is the nodes, the farms dataset, where we have the position, the geographical position of each node, and the productive class of each node, if those are farms. Also, we have the movements dataset that register daily movements of buffaloes with the origin and the destination nodes, the species that is moved, and the date of the movement. In the plot on the right, we have again the map, and each region is colored according the most common productive class in the region. And instead, each node, each dot, represent the productive class of this single farm. We have a prevalence of dairy farms, again in this southern central part of Italy, while the rest of Italy seems to have a prevalence of beef farms. The distinction between the productive class will be important also in our simulation. In the following, I did not consider the slaughterhouses in our network analysis, since they were not, I can say, relevant to the diffusion of the pathogen and were kind of biasing the analysis. Now, since the data were kind of consistent between the 4 years, we started with a first analysis, aggregating the data and considering the whole dataset altogether. On the plot on the right, we can see on a log-log scale a blue line that represents the out degree of the nodes, and the green line that represents the weighted out degree of the nodes, weighted on the number of animal moved. Here we can see how there are no nodes with a huge number of movements out from the node, and also the number of animal moved doesn't seem to be that big, as the green line doesn't differ that much from the blue line. Considering again the aggregated data, we tried to found the relevant component of this network. And in the map, we have that the red dots are the components of the greatly strongly connected component, and the blue ones are the the farms of the giant weakly connected component. We have a similar behavior in both the strong and the weak case, as we have one principal really big component with a size of more than 500 for the strong case, while the second component is really small in size. For example, in this case, is the second biggest one, and this is just a component. It's just a set of 4 nodes. The same can be said here in the column on the right for the weak component. What we try to do now is to take into account also the time dimension of the data, the date of the movement. So we aggregated the data by week, obtaining this way 208 time steps, that is 52 weeks per year for 4 years. And here we plotted on the left, on orange, the average in degree for the nodes. On red, the average out degree. The average has been done considering only the active node for this type of movement on the week. And in purple, the average weight. The results are similar to what we said before, actually, for the aggregated dataset, since we don't have a high number of movement, as we can see here, and also the average number of animal moved is not that big. And also on the right, we have the number of active links per week in green and number of active nodes in blue per week, and also those values are not that big. It is worth mentioning on the plot on the left how the average out degree is always smaller than the average in degree. This could be maybe explainable by the behavior of some small farms that send the animals to the same big farm, kind of accentuating the animals in a bigger farm. Now, again, with the weekly aggregation on the data, we try to discover recurrent patterns and or motives. And what we did was to take our weekly network and then compare the results with the same network, but with the time steps shuffled in a random manner. What we try to find here were patterns, and by patterns I mean consecutive movements in consecutive weeks that were recurrent in all the network. For patterns of length 4 or greater in both the order and the shuffle network, we found no recurrent patterns. For patterns of length 2, the results of the shuffled and of the order network were pretty similar, and it makes sense since shuffling doesn't make that much of a difference if the length is just 2, because it is just 2 movements. For length of 3, instead, we have some different results between the shuffle network and the length network that we will analyze on the plot on the right. Here we plotted on the y-axis, we have the fraction of recurrent motives, that is number of recurrent motives above the number of total motives. And in our order network, we have twice as many in fraction, the number of recurrent motives of length 3. This could mean that there could be some kind of cyclicality in our real order network that is not found in the shuffled one. Now, after this kind of analysis, we try to answer to the other question that was how a pathogen can spread on this network, or better, can it spread a pathogen? We consider the bubbaline herpes virus. That is a highly infective pathogen, is transmitted by close contact or aerosol. The animal, after that has been infected, it becomes latent after 2 weeks on average. And the animal can return infected if it is stressed. And so here we can take into account the transportation stress the animals suffer when transported, or the exposure to the sun. Exposure to the sun is important. Indeed, in our simulation, you will see we divided the weeks of the years into normal weeks and sunny weeks in order to take into consideration this effect. It is worth mentioning also that this pathogen can infect the bovines also, and a bovines infected with the bubbaline herpes virus can test positive to the test for the bovine herpes virus. Now, regarding the model, is important. We consider a compartmental model with the forms, not the animal, as units. Our farms can be a susceptible farm, the green, an infected farm, the red, and a latent farm, the blue. You can go from a node S to a node I with a probability of infection lambda 1, and it describes the events of receiving from an animal or more animals from an
I lost the sound. I don't hear Giacomo anymore.
Me too.
Okay. Giacomo, can you hear me? Maybe can you try your microphone on and off again? We lost you. Now I lost the video as well.
I have the video, but I cannot hear him.
Giacomo, can you hear and see us? So he's moving. Oh, perfect.
Yes.
Brilliant.
Okay.
We lost you.
Okay. That's not good. When?
Near the beginning of that slide, actually. Maybe you can start again from that beginning of the slide when you explain your model.
This one or the one before?
This one. Then the next one, the model slide.
Okay, this one.
Yes.
Okay, so you can hear me now?
Yeah, we can. It's all fine now. Sorry.
Okay, sorry, I don't know what happened. Okay, so we consider a compartmental model where we consider as units the farms. Our nodes are divided into 3 compartments: the susceptible, the green, the infected, the red, and the latent, the blue. You can go from a susceptible node from being a susceptible node to being an infected node if you receives from an infected node, and this can happen with a probability lambda. The same can be happen if you receive from a latent node, and this happen with a probability lambda 1 times delta, so it's scaled by a quantity delta. Now, a node can return to being susceptible. This can happen when the farm is clear and the animals are not there anymore. And this happen based on the average life of the animal. The average life of a dairy animal is 20 years. So as parameter, we considered 0. The average life of a beef animal is 1 year, something more. So we consider as parameter a probability of 1/60. Remember that we are using the weeks as our time period. Now, delta, as we said before, is the quantity that we use to scale the probability of becoming infected if I receive from a latent. That is the probability that a node goes from latent to infected. And it's also the probability of a self-infection of a latent node, for example, for the sun exposure. Lastly, there is the parameter that describes the node that goes from being infected to becomes latent, and is a probability of 1/4. In the value column, you can see that some parameters are between square brackets. This describes the grid search that we did. I will present just some of the results here. This is the first results. We did it with, we started from a set of 10% infected nodes between the total selected at random, and we repeated for 50 runs. The little dots that you can see here are the sunny weeks that I was mentioning before. The blue lines are the number of latent nodes. The red lines is the number of infected nodes. The purple line is the sum of the infected nodes plus latent nodes. It is the nodes where the pathogen is present. The shade that you can see behind the lines are the average of the 50 runs. The shades are the max and the mean values. In all the 4 cases where we considered these values of delta, 0.1 for the first column, 0.3 for the second column, and lambda 0.5 for the first row and 1 for the second row, we have the same behavior, maybe with difference in magnitude. And the purple line is always increasing. It starts from a value of 245, for example, and ends with bigger values. So it seems here that this network can support, at least with these parameters and this start, the diffusion of a pathogen. Now, we talked about shared nodes before. Shared nodes are the nodes that have a presence of both bovines and buffaloes. And here, with the same parameters and the same setting and the same y-axis, we have the number, the average, and the min-max with the shade number of the shared nodes that are reached by the pathogen in our simulation. And again, here, we have an increasing behavior also for this particular subset of nodes. We decided then to rerun all the simulation, but with a smaller starting subset of infected, 1% here. Just for clarity, I will, in the next slide, I have the same results, just zoomed, so you can better see it. Just take into account that the y-axis are gonna change. And this is the zoomed plot. Now, the legend is the same as before, and also the value that we used. And here, again, we have the same type of increasing behavior, maybe again, with a difference in magnitude, but what we are interested about is the slope of these curves that seems to be increasing in all of the 4 cases. And the same, it seems that can be said again for the subset of the shared nodes, the bovine and buffalo nodes here, that seems again to have an increasing behavior in all of the 4 cases. And so, to conclude, what can we say? First of all, we can say that the Italian buffalo is a non-negligible entity that so should be considered in the analysis. It seems also that can support the diffusion of a pathogen, like for example, the bubbaline herpes virus 1 that we consider. And its role should be also considered when analyzing a pathogen spreading on different networks, like for example, the bovine one. What can be done from here? These are just suggestions of future direction. For example, we could analyze both networks together, the buffalo network and the bovine network, maybe with a multi-layered approach. Another idea is to study known method to prevent disease diffusion, for example, the sentinel nodes, and see how they hold on this type of network. A third possible direction is to kind of reverse the analysis that we did here and consider different bovine pathogens that could find in the buffalo network a potential reservoir, a place where to develop. And actually, that was all. Thank you for listening. And if anybody has any question, please, obviously, feel free to ask.
Thank you very much for a very clear talk. While the questions are trickling in, let me kickstart it off again. I was wondering what, just more about the methods or the tools you used for your network analysis, and then for your linking it with the epidemiological model. But first of all, the network analysis.
Yes, sorry, I didn't get the question, sorry.
What tool did you use to carry out the network analysis?
I just use, I use Python and normal mathematical formulas. So I just, for example, for the degrees, I just counted them. For something, I used some libraries like NetworkX just to provide them on a dictionary type of data. And for the others, I just take the raw data and did my own script to carry out the simulations.
Okay. Yeah, because R has for social network analysis has a lot of tools, for example. So I just wondered.
Yes, for Jeff, I could use them for just the network part, but I didn't find any libraries that were satisfying me for the simulation part. So I kind of did everything on the same framework. So I could have the data in a way that I could use them for the simulation and also for the statistics. Maybe for more difficult statistics, I will use some external libraries, but for this I did not.
Yeah. No, there's always a trade-off between you don't want to reinvent the wheel, but you also want to have enough control
Exactly. Yes.
So it's yeah, it's always
Yeah, especially for the compartmental simulation and dynamical time dynamical network, it's difficult to find something that behaves the way that we wanted. So I kind of wrote it from scratch.
right. Yeah. Yeah, and I was wondering more about, so because there's still a way to go with your studies. So you
Yes.
have lots of rooms and to take it forward. So my question was, how much worry is there in Italy about the, buffalo and cattle movement in terms of transmission? And what if you gave an advice to the Italian government in kind of what kind of data they would need to collect, and what would you need to really predict the risk of pathogen spread? What would it be?
Okay. The answer depends if we are considering bovines or buffaloes. In the sense that for buffaloes, for example, the pathogen that we consider is not often tested since it does not have that big of an impact on the buffaloes, but the equivalent, so the bovine herpes virus, has a huge impact on the bovines. So the idea for the government for the buffaloes would be just has a beginning, maybe test more animals, and also make sure that the data that we have, because these data are mandatory, you need to say which animal you are moving from where to where. Make sure that these data are the correct ones, because maybe someone makes mistakes or invents things. And for the bovines, there is another important things to consider that are, at least in Italy, the pastures that are not that well registered. For example, we don't have the geographical location, the exact geographical location of the pastures in all of the Italy. So we know maybe the region or a macro area, but we don't know exactly where they go. So if we need to take into account also infection from wildlife animals, we cannot do that with max precision because we don't have that type of data. So the answer are two. From one part is provide better data or provide data that are not here in that moment. And the other one is start to consider and test more maybe the animals if you are interested on this.
Okay, thanks. Pauline has a question. Pauline, you want to ask that directly?
Thank you, Giacomo, for the talk. It was really interesting, and I have a question about the epidemiological model part, and especially about one of your assumptions. I think, if I have well understood in your table, that you assume that dairy farms cannot lose infected animals because you put a 0 for the mu, and I was wondering why, and why beef farms can get rid of the infection while dairy cannot.
Okay. Maybe I forgot to repeat it when you lost my audio. The idea is that the dairy animals have an average life of 20 years. And so since we are considering the farms as units and not the animals, this event is when you clear the farms, you sell all the animals or something like that. And since the dairy animals stay in the farms for in average 20 years, and we consider 4 years, we decided to put 0 as parameter because it's kind of impossible event. Instead, the beef animals have an average life of 1 year, and so we put 1/60, considering the weeks as time values, because it's the average value of the animals, and often they are taken together and sold together.
And I have a second question, if I can ask. I was wondering if you look at which nodes contribute the most to pathogen spread in your epidemiological model, and what are their characteristics?
Okay, it's not here. It depends a lot, obviously, on the starting nodes. The idea is that, obviously, the nodes with the higher out degree and higher in degree are the most important ones. But the reason I have actually I'm going to take the in degree plot. Sorry. Okay, here. there aren't that many nodes with a big in degree. There is just this node here, that is a node with a really high number of movement in. So if you receive animals, you are the most probable to being infected. But this node has almost has a really low number of animal going out, and the others are pretty similar, as we saw also for the out degree plot before. So there is a node with a huge number of movements or something like this. There are bigger nodes, of course, but their impact is not that relevant. It was not possible to find one node that could impact the network that much. I mean, I did a bit of also percolation analysis, and there wasn't that node that when removed stopped the spread of the diffusion. But it's obviously a point that I could expand in the future.
Okay, great. Many thanks.
Okay, thanks.
Thanks. So that concludes the session. I would like to thank all three speakers for giving really high quality presentations.